This work was made in collaboration with Jason Rodriguez, Jose Fernando Rodriguez, Luis Gomez, and my name is Jhan Nicolás Martínez, and I will talk you about the astrophysical solutions in generalized SU2 Proca theory. Well, the contents of the talk are this. In a first step, I'm going to give you a little introduction to the problem. Then I will explain the Ostrogradski's instability. I will show you the Lagrangian of the theory, and finally, I present you our results and the prospects of this work. Well, neither the Bacon-Einstein equations nor the Peirce-Mills equations have non-trivial static globally regular solutions. But Barnick and McKinnon, in this paper, found in 1988 a family of numerical solutions of the coupled Einstein-Mills equations, statics, and globally regulars. Well, in other hand, we have the generalized SU2 Proca theory. This is a modified derivative theory, which introduces a vectorial degree of freedom, which enjoys a global internal SU2 symmetry. The theory has been built following Hordenski's spirit because it avoids Ostrogradski's instability. So the theory exhibits properties, for example, that make it a candidate to describe primordial and late inflation while satisfying the restriction on the gravitational wave speed. So we are here in a position to study the generalizations of the Cage boson stars found by Barnick and McKinnon, because the theory needs to be validated at astrophysical scale. Well, these solutions could eventually contribute to the matter content of the universe. Okay. Well, the Ostrogradski's instability, as you know, so a necessary condition to avoid the instability is removing contributions higher than second order in the equation of motions of the theory. Well, this is a first ingredient to build the theory. The second one is related to this, to the universe. This is an image from the Sloan Digital Sky Survey. At cosmological scales, the universe is homogeneous and isotropic. So appears to guarantee the use of vector fields to describe the universe. And that's when the generalized SU2 Proca theory born. So here I present you the Lagrangian of the theory. This is the Einstein-Hilbert term, the kinetical term of the vector field. This is the mass term of the vector field. And these parameters, alpha sub 1, alpha sub 3, chi sub 1, chi sub 2, chi sub 4, chi sub 5, and chi sub 6 are free parameters of the theory. But in this form, the theory already satisfies the constraint on the speed of the gravitational waves. So, well, the explicit forms of these Lagrangians is here this way. You can see this the reference from Hinson to see these explicit forms. So, to find the static and spherically symmetric solutions, we start using this line element. This is the more general for the static and spherically symmetric case. Epsilon and rm are functions of derivatives. To the profile of the vector field, we found in the literature this profile found by Witten in 1975. 77, sorry. This is the more general vector field profile for a vector field with global internal SU2 symmetry. But in our case, we just use the Topf-Polyakov magnetic answers given by this last equation, and we redefine phi sub 2 as V, as you can see here. So we proceed to find the field equations. We define an effective energy momentum tensor, as you can see here. This effective energy momentum tensor has contributions from all these terms except but the terms with chi sub 4. Chi sub 4 doesn't contribute here at all, so we couldn't find particle-like solutions with this parameter. So we found the series solution around the origin of the physical quantities. For example, here is the function of the vector field profile. The pre-parameter v sub 2 is a parameter associated with the effective central energy density of the fluid by this equation. We find the series solution around the origin of the mass profile 2. You can see it here. And for the zero component of the metric, the epsilon function, we had here the series solution. We found the series solution around the spatial infinity 2. Here, the pre-parameters are b sub 1 tilde and m sub infinity. Well, this is the series expansion for the vector field profile, and this is the series solution for the mass of the configuration. Well, we use it to find numerical solutions. We construct initial data at r equal to 10 to minus 3, and we adjust always the parameter b sub 2 by shooting global solutions, always looking for the asymptotically flat solution. So graph, this is the mass profile for the case of Einstein-Mills or case. And when we have the parameter chi sub 1, for example, in this asymptotically flat solution, is this red graph. As you can see, the mass of the configuration in the Einstein-Mills case is near than 0.97 solar masses, but in this red case is near than 0.6 solar masses. The parameter chi sub 1 change the effect central density 2. Blue line is the case of Einstein-Mills, but with chi sub 1 equal to 1, we have a higher effective central energy density. We found a equilibrium configuration with chi sub 2. In this case, we have chi sub 2 equal to 1. In this case, the mass of the configuration was near than 0.7 solar masses, and the effective central energy density increased in this case too, just like the previous case. In the case of chi sub 5 equal to 1, for example, we found that the mass of the configuration was near than 0.
Jhan, we have experiencing some problems with your sound.
Density in this case decreased. For the case of consider the mass of the configuration decrease here near to 0.53 solar masses, and this is the lowest value of the central effective energy density that we found to these cases. And finally, we explored the parameter alpha sub 3. We made it equal to minus 0.1, and we found that the equilibrium configuration in the asymptotically flat solution was very similar to the case of Einstein-Mills. The orange line and the red lines are almost the same, but only the effective central energy density of the configuration was a little higher than the case of Einstein-Mills. Well, these solutions are made of only the metric tensor and the vector field. So all the cases constitute particle-like solutions. Notice that in all the cases, the effective central energy density took values between 10 to 19 and 10 to 20 kilograms per cubic meter. And these configurations are made of vectorial bosons. That's why they could eventually contribute to the dark matter content of the universe, because they are not coupled to matter. when we proceed to see the behavior of the metric, we found that there was in all the cases a behavior very close to the Nordstrom solution, just outside the
5 minutes.
objects, as you can see in this label. Okay, thank you. As you can see in this label, we tried many cases, and in all the cases, we found that the behavior was the same. And in a far field, we can think that the metric becomes approximately equal to Schwarzschild's solution. For the case of the mass of the vector field, we didn't explore that parameter because in this paper of Green, it was found that mu has a maximum value of 4 times 10 to minus 2. Well, then the effective central energy density leads 2 orders of magnitude. For example, this is the case when we vary chi sub 5. And we found that only chi sub 5 and chi sub 6 had the behavior that we want. So we proceed to add baryonic matter with energy momentum tensor of a perfect fluid. As you can see here, we use a polytrope equation of a state with polytropic index equal to 1. And we construct the values. Well, we vary the effective central energy density in function of the parameter chi sub 5 and the parameter chi sub 6. And for example, notice here to chi sub 5 that for values higher than 5, the effective central energy density already decreased 2 orders of magnitude. That's because we want to have effective central energy density in the same order of the central energy density of baryonic matter to model neutron stars. And for the case of chi sub 6, for values higher than 3, we found the same behavior. So in this moment, we are doing mass radius and mass central density of the matter relations to model neutron stars, but only with chi sub 5 and chi sub 6. Well, we would like to study the stability of the solutions, because in the case of Einstein, Jhan Mills, or Barnick McKinnon, the particle-like solution stable, but we hope to find a stable configurations in the well, we would like to study black hole solutions in this theory too, and why not that's particle orbits, lensing. Well, that is. Thank you.